Okay.
Okay. Good morning, good afternoon, good night for everybody that is listening us in this webinar, senior webinar. It's a pleasure for our Compat International have this conference from Dr. Konstantin Kovler. Thank you very much, Dr. Konstantin, for this moment that you are offering for the Alcompat International. Also, I would like to say thank you for hosting that's have an effort to stay with us and offer for everybody this very interesting conference. Thank you. I would like to pass the word for the Pedro Castro as general, how is the name in English? General
Director.
General Director of Alcompat International. Thank you very much. Please, you can continue.
But before me, I'd like to hear some words from Julio. Thank you, Enio. Okay. Julio, please go ahead.
Thank you, Julio.
You are muted, Julio.
Your microphone is
okay. It's okay.
Closed.
Thank you, Konstantin, for your being here. We appreciate your participation in this edition for the session webinar. Thanks for that. I'm Julio Medina. I'm a technical relationship coordinator in Holcim. Okay, welcome to everyone. Thank you, Doctor.
Thank you, Julio. It's my big pleasure to introduce with you to Dr. Konstantin Kovler. As you remember, he was our last senior webinarist last year in 2023. And as you remember, Konstantin is head of the Department Building Materials, Performance and Technology. He is at the National Building Research Institute at the Department of Structural Engineering and Construction Management and Faculty of Civil and Environmental Engineering at the Technion Israel Institute of Technology. Costa is also co-leader in the Research Center Sustainable World at Guangdong Technion. Costa, it's a big pleasure to have you with us again. It's an honor to have you here, and we thank you for your generosity to share your knowledge with this audience from Alcompat. Thank you, and please, you can take the word.
Thank you very much. Thank you, Enio. Thank you, Julio. Thank you, Pedro. Thank you for this invitation. It's my pleasure and honor to share with you, with your audience, some thoughts about the challenges we have in construction industry and also in academia, which deals with research projects to help the industry because we all face some difficulties to recycle huge volumes of industrial byproducts accumulated by different kinds of industry. And as you know, the construction industry is the biggest one which can accommodate these byproducts. But unfortunately, many byproducts accumulated in disposal sites are contaminated with different kinds of contaminants, impurities. And I would like to tell you about some experience and bring more examples of mainly mineral materials, mineral byproducts, industrial byproducts, which can be successfully utilized in construction. So this is the topic of my presentation. I'm representing again the National Building Research Institute, which belongs to the Technion, Israel Institute of Technology, and also affiliated with the Faculty of Civil and Environmental Engineering. By the way, do you see my mouse moving? Very good. And then, but this is not only the property of the Technion. we are a joint venture between the academia, I mean the Technion, which is a leading polytechnical university in the country, and the ministry, governmental ministry of construction and housing. So most of the research projects, mainly of applied character, going through our National Building Research Institute, and I'm also heading one of the departments, 4 departments, which is called Building Materials, Technology, and Performance. Performance means all kinds of building physics and calculations, which are not exactly static or dynamic calculations of buildings and structures, but some other physical equations we are using for predicting the mass transfer, heat transfer. It's also related to thermal insulation, acoustic insulation, fire resistance, and other interesting and very important things. So let me start with the next slide. This is a short outline of my presentation. I will start with some motivation, again, speaking about disposal sites and huge volumes of the industrial products accumulated there. And then I will speak more precisely about different contaminants, starting with chemical ones and going through radioactive contaminants. They are different. And bringing you many different examples of industrial byproducts contaminated, mainly with norm. I will explain you later on what does it mean norm. Norm has double meaning. I will speak about it later. And then I will finish with just a philosophical question, how we can proceed from here. So motivation. I will start with disposal of very, very large amount of solid byproducts. This become a serious environmental problem, not only in our small country, but also in Mexico, in the United States, in China, in many, many different regions in the world. Most of them are disposed as landfill. And in my opinion, and that's not only my opinion, this is a practice which is under examination for environmental concerns. We have to be very, very concerned about this practice, landfilling. Land disposal poses long-term potential environmental risks. But look, please look, this waste, as we understand, should more likely be regarded as resources, not waste, but resources, placed in the wrong place. I would like to explain what I mean by the word waste. Waste in principle means no use. But let's say somebody, maybe somebody of the audience will come in 5-10 years or something and will suggest a new technology, a new approach to recycle this waste. Then this waste cannot be seen as no-use waste. If it can be recycled, why not to utilize in the construction and in some other industries? So we see that considerable research is being conducted worldwide on the reuse as recycling of waste materials to deal with the increasing threat of the release of toxic elements to the environment, or to streamline the present waste disposal techniques by making them more affordable. So economics is a very important part of any development. An economically viable solution should include the waste utilization for new products rather than land disposal. This is a trend, and we are strongly supporting this trend. Construction industry. Yes, we are very much concerned with different kinds of contaminants in construction. And of course, you can understand the best way to handle toxic industrial wastes is to avoid their generation. This is the best solution, but it's not possible. Government should promote and support educational and training programs and establish policies that encourage waste minimization and reuse, recovery, and recycling. So this is a very important role of government. Why I'm speaking about government and about regulation, about environmental authorities, because we cannot come to the shop and ask, please sell us 1 cubic meter of clean air, or 1 kilogram or 1 ton of clean earth, or clean water, because these environmental terms is something which belongs to the society, and who is taking care of the regulation is the government, regulatory authorities, mainly environmental authorities. So government should be somehow involved in regulation and support the research. So regulation and monitoring of collection, transportation, treatment, and disposal of toxic industrial waste is crucial. And then let's speak in more detail about different kinds of contaminants, chemical ones and radioactive ones. So starting with chemical ones. What are the chemicals of concern? This is very, very brief explanation and brief list of the chemicals of concern. But as you can see, as you can know, we have a long list of chemicals used in construction and in other sectors. So this list of concern can include thousands of different names, different titles. We can understand easily that it is a result of rapidly accelerating urbanization. Please look, the global construction sector grows by 3.5% annually. I'm speaking about 5 years from 2018 to 23, 3.5%. But the chemical industry is growing much larger. So you can see that chemicals market only for construction, estimated to grow by 6.2% annually. And then you can imagine that how many chemicals, and many of them contaminated, we have to take care of. Many of the sector's products are chemical intensive, and some of the chemicals used in construction can cause severe harm to human health and the environment. What are the chemicals of concern? This is very brief list. Please, because of the lack of time, I cannot and I should not come to much detail in listing them. But I'm starting with heavy metals, lead, mercury, and many others. Lead, for example, is a toxic heavy metal that can cause serious health issues, especially in children, because of the long exposure. It has been commonly used in paints, pipes, soldering materials in older buildings. Lead, by the way, was extensively used by ancient Romans, as you may know. Asbestos, it's another issue. Asbestos is banned in many countries. But I know that in Canada, for example, it's not banned. I don't know the situation in Mexico. Maybe Pedro Enyo can help me and tell about the asbestos, but I suppose the asbestos is also banned. Am I right? In Mexico.
Yes, you're right.
Asbestos is a naturally occurring mineral fiber that was once widely used in building materials for its strength and heat resistance. So it's perfect material from the point of view of mechanical properties and heat resistance. But exposure to asbestos can cause serious lung diseases, including cancer. So I'm speaking not only about workers, I'm speaking about population. What are other chemicals of concern? I'm continuing the list. The list is again long, but I selected a few organic chemicals. Starting with formaldehyde. It's used in adhesives, glues, resins, in plywood, particle board, and insulation. A very known carcinogen. Can also cause respiratory issues and other health problems. PVC, polyvinyl chloride, type of plastic used in pipes, flooring, and window frame, can release harmful chemicals, including dioxins, during production, use, and disposal. VOC, volatile organic compounds, is a chemical that can evaporate into the air from building materials such as paints, varnishes, and adhesives, contribute to indoor air pollution. And other organic contaminants, phthalates and flame retardants. So I can continue this list, but because of the lack of time, I don't want to do it. What is interesting, most of the chemicals of concern are plastics. And this is the diagram which illustrates the severeness of exposure to plastics. As you can see, PVC is the most hazardous. Plastics with other plastics with highly hazardous additives, and other and polyethylene, polypropylene, and bio-based plastics. We prefer to use this end of the scale, green one, and avoid using the plastics which belong to the left end of the scale, left on the scale. This is a reference for this diagram. Then the question is what to do with these chemicals of concern. Of course, very easy solution, because we have so long list of chemicals. Why not to use another type of chemical which is not of our concern? So this is very easy to do it. But for this, the consumer, the manufacturer should be aware about potential risks and make some calculation. This paper in particular suggests some calculative models how to estimate the lifetime cancer risk and hazard rank of the chemical of concern. But look, I'm frank. This is very difficult task, because we have so many different kinds of chemicals, and the risk is going to be very widely changing from one to another chemical. But these authors suggest some number. If the lifetime cancer risk, it's a probability to have this cancer during the lifetime, is more than 10 in -5 power, then this is the list of chemicals in various building products of high concern. But look, some of them, for example, formaldehyde in several wood products, can have lifetime cancer risks much higher, several orders of magnitude. Please look at the power. Here we see -5, and here we see -1, which is dramatic increase of the cancer risks. So we have to be very careful. So now about mineral byproducts, which can contain some chemicals of concern. This is the citation from Jeff Rach, recycling coal ash. And you know what is coal ash. This is very popular byproduct which is widely used in construction, because we consider this additive as a resource. By the way, we know that we have a trade between different countries. For example, Spanish ship and sell some fly ash to Portugal. And we have many interesting examples of the trade between the countries. So this is good and very useful resource. It can improve the properties of the final product of concrete, for example. It can increase the durability of the product. It can improve the fresh properties and improving rheology of fresh materials. I'm speaking about cementitious materials, and so on and so on. But recycled coal ash and also shredded tires, which are solid waste solution, they create largely unexamined by potentially serious public health side effects. So as a result, we have a massive stream of hazardous waste disposal masquerading as a beneficial use. So please be very careful of using byproducts, because many of them, including these very popular products like coal fly ash, I will speak about coal fly ash later on in the presentation, they can contain chemicals of concern. I'd like to share with you by some thoughts about tire-derived products, for example, in flooring. As we know, waste tires and their accumulation is a global environmental concern. These tires are not biodegradable, unfortunately, and globally, the amount is estimated by 1.5 billion tons. So the construction applications of recycled tires, and recycling is a very good solution for these tires, include tire-derived aggregates, which are called TDA. It's abbreviation of tire-derived aggregates, and the mixtures with soil, tire sidewalls, etc. By the way, we have ASTM standard. This is the number of the standard, which regulates the practice for use of scrap tires in civil engineering applications. So it's known. But recently, our institute got a request to assess concerns of using the mixture designated for flooring infrastructure system with a high thermal and acoustic insulation. And this is very good to have because we have the flooring system. For example, the upper layer consists of tiles or any other flooring elements. But below this upper level, this company suggested to use this mix together with some other material like aggregates made of dolomite or limestone or something like this. And this is very good solution for having better acoustic insulation. And also this reduces the load on structural foundations because this material is lighter compared to natural sand and gravel, which is a very popular material for using as a substrate for flooring. Now I would like to ask, maybe some of the audience can say something about concerns. Do we have any concerns? Maybe there will be some question from the audience or opinion or from the organizers. What kind of concerns can we have? Any ideas? I would like to provoke some discussion, if possible. If it's possible, Pedro, what do you see? What do you think? Maybe you can answer. You can suggest something. It's just thinking loudly. Please don't be afraid. Any concerns? I would like to provide some tips. If we speak about emission of different VOC, volatile organic compounds or something, this is below the upper level. Below the upper level. So what can happen during the fire? This is one of the concerns. Fire resistance of such mixture can be a problem. And then we requested from the company before they are coming to us with more ideas and asking to make a, let's say, approval or disapproval of this solution. test this material for fire, exposed to very high temperatures, and see if this tire derived material can burn by itself. Because if it's burned by itself, the temperature is not reduced very, very quickly. It is kept constant for a long time. And this was one of the concerns. Just to tell you, the result of the test was positive. So, and we decided in the institute that we can improve this application. But there is another concern. What is another concern? I think many of you heard about underfloor heating. And then the emission of this VOC, for example, volatile organic compounds, is dramatic under heating. And then, just to come to the conclusion, we gave them approval under limitation, under condition that it will be not used in the floors with underfloor heating system. Now I'm coming to radioactive contaminants. Most of my research was in this topic. So we have a special lab dealing with measurements of radon and other naturally occurring radioactive materials. We call them briefly NORM. But NORM, as I told you before, it has double meaning. NORM as norm, of course, and NORM is abbreviated term, naturally occurring radioactive materials. When it comes, where it comes from? It is a part of the radiation, so we cannot avoid the exposure to natural sources of radiation. We have natural sources everywhere, starting from cosmic radiation, solar, radon, which we can breathe at homes, and radium and thorium. By the way, this is a mistake. It's instead of 2 to 6 radon, it should be 2 to 6 radium. Uranium, thorium, terrestrial radionuclides. So every material which is of mineral origin extracted from the earth, and in construction we have many different kinds of materials of this kind, contains this or that concentration of these natural radionuclides. Natural radionuclides are classified and divided by 3 categories. We have one, it's not one element, it's a whole series of disintegration, starting from uranium-238. The next series starts from thorium-232. And we have, how to call it, single soldier. It's a potassium-40, which is a single radioisotope, radioactive one. And then to have an assessment of the total dose, the literature uses so-called radium equivalent activity, which is proportional to radium, thorium, and potassium concentration. The units are becquerel per kilogram. This is a unit of radioactivity of the material, specific radioactivity, divided by kilogram of mass. But the worldwide average concentrations of these elements is 40, 40, and 400, respectively, for radium, thorium, and potassium. By the way, this series is called very often radium series because radium is very important elements in the middle of the disintegration chain. But as you can see from the numbers, and I believe that most of the audience are engineers, they are very sensitive to numbers. Numbers play a very important role, and we can see the difference quite clear. 400 becquerel in the earth of potassium. So we can imagine that potassium power as gamma emitter is very weak. So we expect a lot of potassium in the earth, and as a consequence, in the building materials produced from these minerals extracted from the earth. And then you can see the coefficient. We multiply the concentration of potassium is very, very, very low because the role is minor. But thorium and radium, they are very, very powerful emitters of gamma radiation. And this radiation is the most penetrating. To protect from gamma radiation, we need to build a very, very thick wall. Let's say it's used in reactors, let's say 1 meter thickness. Other types of radiation are very weak. Beta, we can protect by just a hand, and alpha, we can protect by piece of paper. And that's all. This is very weak radiation. By penetration force. Now, let's say building materials as gamma emitters. These materials, as I explained you before, generate different radionuclides belonging to this disintegration chain of uranium. Radon is in the middle. Immediately after radium-226. Immediately after radium, we have radon, and radon is a gas. All the rest are aerosols, metals. But radon is very important. It is responsible for the most of natural doses. The population and workers, of course, working in workspaces can get from being exposed to natural radiation. About 50% of natural radiation comes from radon. And radon is very hazardous because we can breathe this radon gas. It has about 4 days of half-life. It's enough to come to the lungs and continue to disintegrate inside the body. So we have to distinguish between external radiation, which is a gamma radiation, and internal radiation, which comes from radon. Okay, this is a series of thorium starting from 232 thorium. Also, we have in many products, bricks, concrete, gypsum, different kinds of minerals, ceramics, by the way, natural stone product, tiles, and so on and so on, and potassium 40. But here you can see something which is not natural. This is cesium-137. Cesium is artificial radionuclide. Why some countries are concerned about cesium as well, like Finland? And the reason is very, very simple. Because as you may remember, in 1986, on 26th of April, there was disaster, ecological disaster, environmental disaster, disaster in the global scale happened in Chernobyl explosion of the Chernobyl atomic power station. And the cloud containing different artificial products, fission products, first of all cesium, flew all over the globe 1.5 times. Why? Because Americans measured the concentration of cesium twice. So, but this is not a problem for many countries, only for the countries which are very close to this Chernobyl accident. And in the earth, in minerals extracted from the local materials, they have some cesium as well. Now, I would like to tell you something about the units, because we need to establish a common language. Radiation basics. I'm starting with units and with just a moment. With absorbed dose. So we need to speak in the terms of dose. Dose is the amount of energy absorbed by the body. by the body, by the material. So this is joule divided by kilogram of mass. The absorbed dose, which is called D, designated D, was explained by Dr. Gray. So, and the international unit of the absorbed dose is a physical parameter, is Gray, honoring this researcher. Then we need to introduce equivalent dose, H, which is much more important for speaking about radiation protection of the population. This dose is measured in sieverts. Sievert honoring this researcher called Rolf Sievert. He's from Sweden. This H is equal to the integral in which we have absorbed dose in grays multiplied by some factor, and this factor contain different factors inside. So the factors dependent on the sensitivity of different organs of the body and particular radiation type. For example, coming back to alpha, beta, and gamma. For gamma and beta, the coefficient taking into consideration particular radiation type is 1. So no need to multiply 1. But for alpha is 20. Yes, I told you about the penetrating power. It's very weak. But alpha particles, which is a nucleus of helium, it contains 2 protons and 2 neutrons, is a relatively heavy particle. In spite of the fact that it doesn't penetrate too far, but when it is inside the body, for example, by breathing radon disintegrating with the production of different progenies, with daughters. And many of these disintegrations are coming with emission of alpha particles. And the distance between cells of lungs and the neighborhood is microns or even less than microns. So the distance doesn't make it doesn't matter. And then in this case, alpha is very sensitive, is very powerful type of radiation. Now about radiation in daily life, and then you can see I'm speaking about effective dose in millisievert, effective equivalent dose in millisievert, because sievert itself is very high unit. Just to tell you, in the epicenter of Hiroshima bombing, maybe you know the story of bombing Japan by Americans in '45 in August. There were 2 explosions in Hiroshima and Nagasaki. The people who were exposed to the radiation from this atomic bomb in the epicenter of nearby was exposed to 1 sievert, and all of them died with very short time, within very short time. So sievert is very high. Please look at the unit. It's millisievert. 20 millisievert per year is a regulatory dose limit for workers. You can ask, what about the population? What about us? We spend most of our lifetime inside buildings. 80 and even 90%, especially during the corona, the people spent longer time inside buildings. And most of this time we are exposed to radiation, natural radiation from the building materials. Look, this is annual dose limit for general public, except medical exposure. It's 1 millisievert. So this 1 millisievert is a kind of holy number which is used widely in regulatory authorities for limitation of radiation dose for the public. But this one is a part of all kinds of natural background radiation. We cannot avoid exposing to cosmic rays, to buildings, radon, and food drinks. But one should be limited. Should be limited as an annual dose limit for some practice. I don't want to go into details. What does it mean, one? But when we come to building materials and the regulation concerning exposure to natural radiation from building materials, we have to limit every component of this radiation by 1 millisievert. And then you can compare with the numbers from air passage from Hong Kong to North American, transatlantic or trans-Pacific flights. They're very long on very high altitude above the sea level. It's not neglected. It's not neglectable. You see, so this is the reason that stewards and pilots, they have good bonuses, even series of bonuses, and they can retire in a relatively young age, by the way. So the regulator considers this exposure. About average effective dose from single chest X-ray. It's something which is not much. Much more we can have from tomography, computer tomography, for example, CT. You know what does it mean, CT? Now, about risk of death, how the regulatory authorities calculate the limits. This is something which is may be very sensitive for the audience. I apologize for very sensitive picture which comes immediately. This is a type of the diagram illustrating the dose response curve. This is the area of the high doses, starting from Hiroshima, Nagasaki, and so on and so on. We are not here in building materials, of course. High doses lead to very short lifetime. If the people are in epicenter, for example, like this poor person, so this it was exposed just in the distance of 3,000 meters from the epicenter, from hypocenter, and you can see what does this radiation make with the body. So it's almost immediate death. Many let's say fire workers, which wanted to protect, were obliged to protect the reactor in Hiroshima, in Chernobyl. They died not immediately, but in 1, 2, 3, 4 weeks. The doses were lower, but still high. So what about the medium range of this dependence? This is a medium doses. We have a lot of statistics. It's a lot of literature available. Most of the literature sources analyze the doses from uranium miners exposed to radon and other radiation sources. And this is low doses. In building materials, we are here in very low doses. But look, this is maybe funny for you, but if you eat some banana, you have to understand that banana is very rich by potassium. And the part of potassium, K, contains very small amount of radioactive element, radioactive isotope potassium-40. If you can check in the periodical table of elements, what is the mass of atom of potassium, average mass, it's 39 point something. So it's a little bit higher than 39. Why? Because one of the isotopes of potassium is 40. And look, radiochemistry is like mathematics. We know well that every gram of potassium is equivalent to 31 becquerel. And becquerel is 1 disintegration per second. This is a unit of radiation. And it's you see, if a man weighs 70 kilograms, so we can imagine that, for example, 175 gram of potassium is in our body. So it's equivalent to 54 kilobecquerel. So it's something. But again, nobody died from potassium from eating bananas. So please don't be in panic. Now I'm speaking about this linear curve, which is called linear non-threshold curve, starting from high doses, low, medium doses, and low doses. But for low doses, there is no evidence that the people die from being exposed to low doses. What the regulators did, because they have no data, they decided to extrapolate this curve towards zero. It means this curve doesn't have any threshold. In other words, every even small increment of the dose of radiation can be harmful. And the hazard is evaluated by the slope, by the inclination. Every increment by 1 millisievert per year is equivalent to risk of untimely death by 50 cases per million people. It means in addition to natural death rate, mortality from cancer, natural mortality is about 200 per million. It's natural. But in addition to this, 50 people die from this 1 millisievert per year. And it depends on the dose. Then you see, 1 million people is exposed to 1 millisievert. It means additional 50 cancer deaths over the normal 230,000 cancer deaths. And then this curve represents the very important term used in regulatory authorities. It's called ALARA. ALARA is abbreviation of as low as reasonably achievable. I just try to explain you what is the philosophy of regulators. We cannot avoid exposure to different kinds of natural radiation. Nothing to do. We're exposed to medical radiation dose. We're exposed to transatlantic flights, and so on and so on. So we cannot require zero. And then the question, what is reasonably achievable? And this is the question the scholars are thinking for dozens of years. What should be done? Where to cut this curve? What is allowable? And the allowable is reasonably achievable. What is reasonable? This is an interesting issue, which is a very controversial issue. Now, the principles of the limitation of the concentration of radionuclides in building materials, BM, are simple. First of all, we are speaking about different origin. Natural origin, for example, granite or alum shell concrete, industrial byproducts, which is a focus of my presentation, like byproduct gypsum, waste rock from mining, etc. And we need to limit the use of building materials that cause a significant increase in indoor radon and gamma exposure. So this is the principle. Now coming back to industrial byproducts, which have elevated content of these contaminants. We are speaking about slag, red mud, ash, phosphogypsum, and some others. Slag are different kinds: blast furnace, copper slag, and so on. Ash can be also different kind: coal ash, bottom ash, fly ash, peat ash, oil shale ash, etc. The reason that in these materials, these byproducts, we have elevated content of radionuclides is very simple, because they are produced as a byproduct after some treatment. For example, thermal treatment. Yes, we burn our coal in thermal firing power stations. Most of the coal is organic matter, so it's burned. let's say 90% is burned, disappearing. And then in 10%, we have so-called enrichment of everything which is of mineral, unorganic nature, including heavy metals, including radionuclides. Phosphogypsum is a result of chemical reaction, digestion with sulfuric acid in the fertilizers plant, producing superphosphate, phosphoric acid, and other phosphate fertilizers. So it's a result of some treatment, thermal or chemical treatment. Look, please, at the table illustrating the typical activity and maximum activity concentration becquerel per kilogram. Let's follow the number of radium equivalent, which is a kind of integral of the of all of these three. You can see that the maximum in these industrial byproducts like phosphogypsum, blast furnace slag, coal fly ash is much higher than in normal building materials. They can also include byproducts, but in these products alone, the concentrations are much higher. Then, speaking about the norms, I will use this main dependence, which is widely used in many countries, in particular in European Union. So this is an index, and index should be not more than 1. How to calculate this index? It's concentration of radium divided by 300, thorium divided by 200, and potassium divided by 3000. And this is approximately equivalent to the dose criterion 1 millisievert per year. But this formula is very simplified. Why? Because we test the materials in the lab in the powder form. In reality, building products can have different unit weight. Some of them, like lightweight concrete, are light. Some of them are heavier, like normal, ordinary concrete. So, and in principle, what is very important to understand, what is the total mass of radionuclides in the building, in building products surrounding the people living there. So, and this is not so easy to make this calculation by using different scenarios of exposure. But this is a very, how to say, important step to start with. This is a screening index. If the building material contains more, for example, index is more than 1, then the producer and the consumer should be very well aware about the possible environmental and health issues. Examples. Starting with red mud. I'm not sure if you in Mexico produce bauxites and produce aluminum, but in many countries it's a severe problem, because red mud is a byproduct of production of bauxite, which is a raw material for producing aluminum by this process. And this is a toxic industrial waste. According to the International Aluminium Institute, huge amounts of alumina were produced. The data is not very updated, but look at the order of magnitude. And then we have more than 100 million tons of red mud generated. It's a huge amount. China, I think, is recorder, keeps a record of discarding red mud alone. And this is the disposal site, which is not already disposal site, because this is the picture. I took it from Associated Press, AP, illustrating the red mud dam broken in Hungary in 2010. It's Hungary's worst ever ecological disaster, because a lot of territory was flooded because of the collapse of the dam. So this is very, very toxic. Red mud. You can see some pictures illustrating the disposal sites in Louisiana and Texas. So and this is a real pain for the mankind. What to do with red mud accumulated in many countries in huge amounts. Now, blast furnace slag. Yes, it contains some elevated concentration. This is, by the way, popular material in cement as additive component. Phosphogypsum, PG. It has elevated concentrations of radium-226. And also radon, which comes from a disintegration of radium, is also an elevated emission rate. This is a reaction in the industry, chemical industry, producing HF, not HF, H3PO4. This is the main product of the phosphate industry. And then they produce superphosphate by reaction between phosphoric acid and the phosphate rock. But look at the amount you can calculate by chemical masses. Stoichiometric calculations are very, very easy to do it. How much phosphogypsum is produced per 1 ton of the main product? It can come in, let's say, 5 or 6 times more than the main product. Now, contaminants in PG, chemical and radioactive. Contaminants of chemical origin are harmful, and they influence dramatically setting time and strength of building binders because of some part of P2O5 is left. They can result in a fluorescence and spots on the surface. They can result in corrosion of steel because phosphogypsum is acidic and makes it requirements of environmental protection, and of course radioactive impurities. Now, please look at the amounts. It's a huge amount accumulated in different regions in the world. Why we don't have accurate number? Because we are speaking about billions of tons. It's not millions of tons like we spoke before about red mud. It's billions of tons. What between friends? Plus minus 1 billion tons. Nothing. So this is the ratio between 1 ton of acid and an amount of 5 or 6 times more phosphogypsum. And the disposal sites are disposal is growing. I'd like to tell you something about Morocco. Morocco is a leading country of producing phosphate rock, and of course they have a lot of phosphogypsum. Only in Morocco they dispose about 50 million tons per year. Israel is a very small country. Jordanians produce more. In Israel, we produce 3 million tons per year. But this is also very, very high number. Americans, Chinese, and many other countries. I think in Mexico, you also have phosphogypsum stacks. I'm not familiar with the numbers, but you certainly know that phosphogypsum is one of the local byproducts. Some pictures. Some stacks are located very close to the populated area. For example, in the vicinity of Sevilla, the city, big cities in Spain. More than 100 million tons is accumulated there. This is Tunisia. This is Florida in the United States. In Florida, they accumulated more than 1.5 billion tons, maybe even more now. This is in Florida. You see how big is the stack? This is in Belarus. This is in South Korea. You see the huge chemical plant producing the phosphate fertilizers, and phosphoric acid, and phosphogypsum is coming in the slurry form to the site, which is 3 kilometers, just walking distance from the plant. And they have some gypsum plant producing wallboards and some other products from this phosphogypsum. This is a picture which was done when I was much younger, more than 20 years ago, when I had this hair, black hair. The current solutions are not effective. We know that fine fractions are richer in radioactivity. You can see the number. So separation between fractions can help, but not much. It cannot provide a radical solution, because in coarse fraction, still in medium fraction, we still have higher concentration of radionuclides, radium. So we have a patented technology in the Technion. This is a patent jointly with Vanderbilt University in the United States, between two universities. And we try to understand what is the problem, how the people tried without any success purifying phosphogypsum from radium. Unfortunately, chemical impurities can be removed, no problem. But radium, and we understood finally that radium is crystallized in the form of radium sulfate. It crystallizes the first, even under recrystallization process, and cannot be washed out, because we cannot wash and remove radium sulfate from the surface of the crystal. It's inside the crystal. We can play with different, let's say, type of hydrates: hemihydrate, anhydrate, and dehydrate. So you see, this is hemihydrate, which is a nice binder. It is a nice gypsum binder, which is a main part of gypsum binder, which is very valuable material, by the way. This is anhydrate, and this is dehydrate, usually as phosphogypsum. But this doesn't help. So what we suggested in this patented technology, we suggested to make chloride complexation at some moderate temperatures to prevent precipitation of radium salts. And the temperature are not so high. You can see a few moments later. And the solution is based on the table of solubility of chlorides and sulfates. As I told you, the problem of radium is radium sulfate. Please look at radium. Radium sulfate is almost insoluble. You can see the number, or the power -4 here. Insoluble. The chloride solubility is very, very high. So if we succeed to transform radium from radium sulfate to radium chloride, and then we can filter the solution, we can separate nicely the solution from the solid residue, and remove all the radium in the solution by filtering. This is the trick we did, but it took some years of getting important development. I would like to go fast because we have no time, not too much time. So this is radon emitted from radium. So in principle, we need to wait a lot of time in the laboratory for having radio activity equilibrium. But we have many tests done, and we have this coefficient, let's say 15% or maximum 20%, so we can take care of this emission of radium. This is the picture illustrating how we succeed to reduce dramatically the peak of radium. We are measuring radium not by radium itself, by their products of the disintegration, by bismuth. This is a peak in raw phosphogypsum, and for example, some thermal treatment, not very high temperature. You can see 100 something, about 100 degrees of centigrade is enough. Of course, simultaneously with chloride reaction with chlorides. This is a calcium chloride concentration, which is our agent. And then you can see increasing the concentration, we have a very good result. So in principle, we have reduction by order of magnitude of radium in phosphogypsum. This is the temperature. You can see about 100, we are satisfied completely with removing radium from phosphogypsum. So we tested both types of phosphogypsum, our local Israeli type and Louisiana type in the United States. And this is a type of scheme we suggested to our producer, but it's very tough to negotiate with the producer, because you can understand, to build the treatment plant, it requires a lot of investment. And then we need to take care about economical efficiency of the plant to produce gypsum binders and gypsum products. One of the solutions, by the way, is to utilize the heat of flow gases, because in the industry we built the plant for producing gypsum near the chemical plant. We can utilize successfully the heat of flue gases emitted by the industry. And the flue gases temperatures are usually high, maybe 400 degrees. So we need only about 100, 120. It's enough. So, and this is the PhD research opportunities, because we succeeded together with our Moroccan colleagues to receive a grant. And we are starting this project in a few months, maybe in October. And we have in the Technion a couple of research positions for PhD. So if somebody in the audience is interested to apply, and this is interdisciplinary project, our colleagues in Morocco, they also have some positions opened in Morocco, but I'm speaking about the Technion. We have some financial support for these PhD students, just to let you know. So please don't hesitate to apply to me or to some other colleagues, which are co-PIs in this project. And we have many interesting applications of purified calcium sulfate hydrates. Hemihydrate is one of them. I'm going quickly. Now coming to the contaminants. Recovered contaminants, by the way, they can be very valuable. For example, rare earths, radionuclides. We can separate radium-223, for example, which is a nice element for radiopharma in medical industry. Phosphates, fluorides. If we succeed to return P2O5 back to the chemical plant, just only this step may justify the investment, some part of the investment for building a new plant. Now about disposal, the key problem is to remove these contaminants. So we have in the waste stream of our process the waste, which is a concentrated waste, concentrated by different kinds of elements, chemical and radionuclides. We have a nice experience with using fine fraction of phosphogypsum. Of course, you understand that some gypsum in this case is lost. Maybe 5 or 10% is lost. But gypsum is very nicely absorbing element. Natural zeolites, artificial zeolite, geopolymers can be used as absorbent. About cold fly ash, I think you know better the situation with cold fly ash, because this is a very popular product, byproduct, by the way, in construction industry. Coal fly ash in some countries is still growing. In Europe, it's reducing. In Germany, for example, they want to shut down all the thermal plants, coal-firing thermal plants, and in many other countries. But in some other countries, like Poland, like in China, it's still growing. So we have coal fly ash. Coal fly ash is very important resource and is used in construction for many interesting applications. This is just some photos of using coal fly ash in some infrastructure projects I was involved in. As you can understand, this is not dwelling. This is just infrastructure projects, and the people don't spend their lifetime in this infrastructure, let's say, structures, tunnels, bridges, pipelines, you see, and retaining walls, and so on and so on. So this is not of the concern for regulatory authorities. But unfortunately, in many countries, in some countries, not many countries, the regulators apply very populist. I'm asking you not to cite me. For example, I'm criticizing severely our Israeli Ministry of Environmental Protection, which announced a few years ago coal fly ash as, please be careful, radioactive waste. And then all our efforts for promoting different kinds of recycling and different kinds of products in construction just gone, because the industry doesn't want to hear about radioactive waste. All of them are simply in panic. Okay, I'm coming to some numbers. We did a national survey on natural radioactivity concrete in our country, which contains fly ash and no fly ash. And you can see the histograms or the populations are very, very close. Why? Because fly ash is very interesting material. Yes, it contains more radionuclides like radium, thorium, and potassium. But radon exhalation, radon emanation is very low, because fly ash is produced under very high temperatures in thermal plant, and particle has a very dense sphere, very dense shell, and it's a glassy phase, which is a good stopper. So radon cannot escape easily from the particles. And then the part of those which is dependent on radon, which is internal exposure, is very low. So it compensates higher doses from gamma. Now the question is very simple. Is it worth to purify fly ash? And the answer is not, our answer. Because why not to utilize fly ash for absorption of radioactive and other contaminants? We did some research trying to produce artificial zeolites, not natural, but artificial zeolites, which is considered as a very good adsorbent. Maybe you know what does it mean, zeolite? Zeolite is a large group of microporous crystalline aluminosilicates made of 3D framework of this crystal and containing silicon oxide, aluminum oxide, tetrahedrons bonded at the vertices by shared oxygen atoms. And this is a typical structure of zeolite. You can see this is the pore of nano size, which is very effective to absorb heavy metals of different atomic radius, including radium, thorium, and other heavy metals. You see, so the pore size can be regulated. You see, so this is nano world. So we are speaking about angstroms. This is very important material as adsorbent. Zeolites from coal fly ash were produced in the laboratories, but not in the industrial scale. So this is the production cycle of producing zeolite. And we try to do some research in our labs using this coal fly ash from one of the power stations in our country. This is a typical chemical composition of our fly ash. And then we can compare synthetic zeolite we produced with natural zeolite. But natural zeolite is not very common. It's hardly available in many countries, and this is costly to import it. Synthetic zeolite to be produced from fly ash doesn't cost money because this is a byproduct. But we need, of course, we need to spend some energy to produce it. We using some caustic soda also, it costs money. So we need to make some cost-benefit analysis before recommending to build a plant. But in principle, this is possible. And the spectrum is very, very similar. So again, the absorption is very good. So we can compare natural one with synthetic one. We have almost the same curve, almost no difference between synthetic zeolite we produced in our lab from coal fly ash and one of the natural zeolites. So these are the XRD diagrams, XR diffraction patterns of fly ash during the treatment. Other thoughts. We have another toxic element produced by chemical industry. This is hydroxyfluoric acid, which is very toxic waste product from phosphate fertilizers industry. The solution in water is a very strong acid. This is also very corrosive in reaction with bases, reacts with water and steam. So this is a painful element, not element, it's compound. So what can we do with this byproduct? We can produce some corrosion inhibitors for concrete. And we tested the efficiency and compared with different inhibitors, classic inhibitors. This is migrating corrosion inhibitors. For example, this is total corrosion by modified ASTM method, G109. I'm sure Pedro is very familiar with this method, G109 in coulombs. So you can see different samples, yellow curves are very low. So, and this is the material which we produced from this very toxic acid. How to proceed from here? And this is one of the last slides. And this is just a philosophical question. I gave you some ideas. And the more important, this will be the last slide, is, in our opinion, would be to find a common language, to establish a common language between the consumers. We are consumers. We are citizens. We are spending lifetime, most of our lifetime in buildings, and we consume these building products. But the producer should be the producer interest should be taken into account, because the technology should be effective, cost effective, and also without regulatory body like governmental authority or environmental authority, we cannot do anything. They have to promote all this research and applications from their side. So we have to close this triangle, and we have to establish a common language between all these three main parties. So this is the end of my presentation. I would like to thank you very much, gracias, for listening, and I'm ready for some questions if any.
Thanks to you, Costa. Thanks for sharing all of this knowledge. It's very, very interesting. We have at least two questions. They are from Fernando Gomez from the US. The first one says, as an asbestos lead inspector, I understand the hazards and benefits of using those materials. What is your
Okay.
suggestion with the nations that do not want to have any type of regulation?
We cannot change the regulation because the regulators are very concerned about the health issues and lung diseases. I remember the time when I was responsible for one of the courses, and I was taking the group of students to visit the plant producing, among different products, asbestos cement products. You see, this is very nice by mechanical properties material and by fire resistance. But unfortunately, after this industry was completely destroyed, this plant, fortunately or unfortunately, so you see, this is a very controversial issue, and the plant was completely shut down. And the territory was contaminated, unfortunately. It's a lot of work to decontaminate the territory, and nothing to do with regulator. We cannot change regulators, but I have some idea what to do with a lot of asbestos cement products in disposal sites. I'm sure that in Mexico you have such disposal sites of asbestos cement products. I'm sure. I know the situation in Europe. Most of these disposal sites are special disposal sites. It's not for construction demolition waste, normal, regular waste. It's a hazardous waste. And almost all of these sites in Europe are full. There is no room to accommodate more and more material coming after demolition. Many buildings were built during the 60s, 70s, in many countries, including in Europe, maybe in Mexico also. What to do? And then the idea is, I just tell you the idea. We have a project. We submitted it to European Union, but it was not funded. But we have some idea. If we take care, of course, with very, very accurate precautions to avoid dusting, starting from collection of the waste from the disposal site, transporting to the plant. What kind of plant? Cement plant. Cement plant. Then if we introduce in very special point in the kiln and taking care of all the steps of this transportation, and we know how to do it, then the material will be completely free from asbestos fibers. The fibers will disappear under very high temperature, special type of temperature, a certain temperature. So if you are interested, some of you are interested, so we can combine our efforts, but the problem is it's very difficult to attract cement industry because we are speaking about investment. Somebody has to invest money. You see, by the way, we have a lab which is helping us. It was a part of our consortium in Spain. They have all types of safety measures to treat the lab specimens containing asbestos cement. So this is my idea as an answer to Fernando Gomez.
If you probably you can respond the questions without, you don't need my intervention. So Fernando Gomez has a second question there, and then Victor Hernandez, and then Carmen Andrade.
Poor nations depend on those materials, and they do not have any other substitution. Look, environmental concerns usually are most important, and this is unfortunately for developed countries, not for developing countries. Developing countries usually neglect by environmental concerns. This is a situation, but again, the awareness of the population, including in the poor countries, is growing. So it will come there as well. Now I understand in many countries, developing countries, poor countries, the people are using contaminated byproducts in construction without any limitation. This is not good. But in 5-10 years, I'm not sure it will continue. The people become aware about the environmental concerns, and the norms are getting stricter and stricter in all the countries. It will come to the poor countries. This is the answer to Fernando Gomez, the second one. Now, should I answer Victor Hernandez? A kind of radiative gel. Are we obliged to change the material to actually use to survive? I didn't understand precisely what does Victor mean. Yes, we have radionuclides. And this is a part of the mineral materials extracted from the earth, and as a consequence, it comes to building materials produced. What to do? And some building materials are richer by radioactive substances. What to do? First of all, we need to be very careful and forbid using them in construction. It means if some, for example, granite, which is relatively rich by radionuclides, maybe you know about it, it can be a problem for countertops, for some other facades, interior, for example. Granite is usually richer by radium, thorium, and potassium. But if this material coming from some country, I don't want to specify the country. It can be China, it can be Italy, it can be some other country, but granites are different. If the concentration of radionuclides is known, then the custom authorities can forbid import this product. This is one of the solutions. Another solution is a local regulation. Don't use this material. If you want to mix the raw material with some else to dilute the concentration of radioactive substances in the finished products, it's also possible. It's another solution. I can give you an example of Japanese. The Japanese use phosphogypsum, but not 100% of phosphogypsum for producing their gypsum boards and gypsum blocks and other gypsum products. They mix it to dilute these radioactive substances with other type of phosphogypsum. Some other type, which can be imported from China, is much less radioactive. You see? So it's a play. It's a play. You can have some suggestions for this. I don't know if I answered. Now I'm coming to Carmen Andrade. Carmen, nice to see you in the audience. Yes, but this is not a question, it's a remark. The second one is a question. Yes, I see this question. My question, there is limit for the proportion of blending material from the health point of view, right? Now that the clinker is lowering, yes, 80%. It can be a problem for geopolymers. It can be a problem for sometimes for cements. By the way, coming back to the project which is going to be funded by USAID, United States Administration for Industrial Development, it's a joint project with Moroccan colleagues. One of the work tasks is to develop special kind of cements using phosphogypsum, but not, of course, not in very high amount in the clinker, in cement. The clinker is reducing and the part of sulfate is increasing. You see, but if the part of sulfate is too high, maybe there will be a problem. So we would like to understand what is the safe limit for using in construction of this type of cements with increased content of sulfate coming from phosphogypsum and with decreased content of clinker. Because slag and phosphogypsum, as I explained you, they have higher concentration of contaminants. good for durability, but what about health? Yes, I try to answer Carmen. If Carmen has more questions, you're very welcome. Then again, Fernando Gomez, correct me if I'm wrong, but the word asbestos comes from the Greek indestructible. Yes, right. Placing it in concrete, aren't we creating another problem? Yes, but my idea was to eliminate completely the formation of fibers, destroy fibers, kill fibers. The problem of asbestos is a very specific size of the fibers, the diameter of the fibers, and the length of the fibers. And then the fibers itself, not asbestos as a material, but the fibers, asbestos fibers is a problem. And then if we burn safely with all safety precautions, we can solve this problem. So cement, which will be produced, will not have fibers. Then I would like to tell you more, because these fibers can contain magnesium, and then it's needed to check precisely the concentration of magnesium, because magnesium oxide is also limited in cement. Pedro, maybe you know it, and Carmen is for sure knows very well the the standards for cement. Magnesium oxide is a very harmful substance. So it should be limited. So then we should be very careful to magnesium. Then Fernando Gomez, he's very active. Thank you very much. What has been done here in the US? We are placing the mitigate asbestos on the golf courses and just placing a sign, do not dig hazardous materials. And I would like to ask loudly, Fernando and other people in the audience, what will happen in the end of the life of this golf course? What will happen in 50 years, in 100 years? Maybe because of the lack of the land, the future investors would like to utilize the land and build something on this contaminated land to remove this golf course, you see? And then they will discover that the land is contaminated. What to do? So this is the problem for the next generation and for the next investors, you see, for real estate, what to do. So this is not a perfect solution in my opinion, just to hide this asbestos under the golf courses. But again, this is my opinion. I think
Costa, we have a last one question from Ivan Escalante. He asks, is floor gypsum also problematic in a similar way as discussed for phosphogypsum?
Please say again, what kind of gypsum is problematic?
Is floor gypsum also problematic in a similar way as
fluorogypsum? Fluorogypsum?
Yeah, fluorogypsum.
Fluorogypsum doesn't contain, to the best of my knowledge, any radioactive substances. It's not a problem. But if this fluorogypsum, which is a byproduct of another industry, also chemical industry, contains some fluoric compounds, this is a chemical contaminant, then I suggest to be very careful and to check precisely what to do with this contamination. So in my presentation, I spoke about two kinds of contaminants, chemical and radioactive. No radioactive contaminants in this kind of is fluorogypsum, but what about chemical ones?
Perfect. Costa, thank you very much. We are going to close our senior webinar with last words from our president, Enio, then Julio, and finally I will give some announcements. Okay. Please, Enio.
Thank you. Thank you very much.
Okay. Dr. Konstantin, thank you. Thank you very much for this very, very interesting conference. I think we are living in a danger world planet. So it's your presentation can everything thinking about this problem. No, I would like to say thank you for everybody that stay in this room. I saw that in a moment we have more or close for 60, perhaps more than these 60 people listen your conference from many countries. So this is a successful of this conference. Thank you very much. And to say thank you for Julio Medina from hosting for this moment that this enterprise offer for everybody. Thank you, Pedro.
I would like also to thank you, Ennio. As I told you in previous time, piacere. It's my pleasure. And thank also the organizers, Pedro, Julio, and all the people who actively participated in the questions and answers part of the presentation and discussion. Thank you very much. It's my pleasure, and I hope to see you, maybe some of you, in the course we are organizing. Can I tell it, Pedro, about the course you are organizing?
Yes.
Yeah,
You
it's
can tell
a
it.
kind of
Say it.
promotion, because we are thinking with Pedro and with Alejandro to organize and the PhD course in Monterrey, Mexico, in October, in mid-October. So please take it into the account and send your students maybe to this course.
Thank you, Costa.
Thank you very
Julio?
much, and see you.
Yeah. Thank you, Dr. Pedro, Ennio. Okay, thank you, Konstantin, for sharing today a relevant topic. It's a topic of great interest to the almost 11 countries that attended the session. Once again, happy to start the new 2024 edition of the Seniors webinar with the Alcompat Association and with you, Konstantin. To the people who are joining us, see you in the next session. Gracias por estar acá. Finally, thank you for the organization, Doctor.
Thanks, Julio. Yeah, I have just 3 announcements. As Costa says, this will be a very, very interesting doctoral course, but it's not only for doctoral students, it's for anyone who has experience in the area of pathology and concrete. You will have to accompany the invitation to attend to this course. Together with this course, very soon we are going to have to start our series of courses of Alcompat, and this time is the first one, Introduction to Pathological Problems. And then in a few weeks, we are starting specifically for students at any level, also for postdoctoral students, the course on how to write scientific articles that is going to be given by Ivan Escalante. And also, we have very soon a very, very interesting joint venture with RILEM. Alcompat and RILEM are going to give this course about the reinforcement corrosion, theory, prevention, and repair. In all of those courses participate professors from many parts of the world. So I encourage all of you to participate, to visit our homepage, and to be registered to these courses. So that's it. Finally, thanks again, Costa. It was a very big pleasure. You made us think what to do in our countries, especially in Mexico. I don't know what to do because we have no standards. that's gonna be a big challenge for us since we are starting to use the byproducts, industrial residues, etc., with no control. So you can imagine. Thanks a lot. Thanks to everybody. And finally, I like to say, of course, as Enyo said, we had representatives from Mexico, Dinamarca, Denmark, Brazil, Venezuela, España, Spain, Argentina, Uruguay, Paraguay, Colombia, Ecuador, Guatemala, Bolivia, and the US. 13 countries on Wednesday 13. Thanks a lot. Till the next time.
Thank you very much. Pedro, I asked you in the chat window to send me the chat if possible, because I had no time to see the questions and comments from the questions I saw, but chat window I could not see.
Yes.
Maybe there
Okay,
was some
thank you very much.
critics I'd like to understand in the chat window. You see, thank you
Thanks.
very much. See you.
Bye.
Bye bye. Ciao.